I want to talk about Sentinel-1 interpretation again. So the synthetic aperture radar signal is a completely different bird compared to the optical signal. We've already talked about this a bit. We've compared the images in the field. There's no such thing as true color for a radar image, and we're not really looking at the intensity of the reflected signal. We are at a bit, but we are looking at the type of the reflected signal and its polarization. So the reflected power is depending on the structure and the dielectric properties of the surface. If you really try to simplify the mechanisms of reflection, then it's these three. So specular reflection, which works very much the same for any kind of electromagnetic radiation. So if you have a flat surface, then you're sending your radar beam at it and the power is reflected away. But the difference is that with an optical sensor, you're flying your sensor at nadir, so on top of the area that you're imaging. But with radar, you are imaging sideways. And so if you have specular reflection, you're probably not recording a return signal at all because the incidence angle is very low. So all the radiation is going away into the universe and you're not recording anything. If you have a surface which is flat, but also slightly rough, like a water surface with a bit of waves, then you are going to get some reflected signal of the rough part, but you're still losing most of it due to the specularity. You can also have a surface where some parts of the surface are reflecting directly because they are facing towards your sensor and others are facing away. In Hungary, we call this the golden bridge. You are watching the sunset, right? Standing on the beach, and you see the red sun sort of reflected on the top of the waves and it's creating a line, right? That's the golden bridge in Hungarian. And this is because every wave with its curved shape has a small part which is exactly at the angle that it's reflecting the sun into your eyes, right? This can also happen with satellite image. So it's also possible that you have a surface where the signal, a small part of the signal is reflected at the regular intervals back into the sensor and otherwise it's dark. So this is specular reflection. The next thing is volume scattering. So if you have a very complex shaped structure, it's going to reflect your incoming radiation all over the place. And the path that the reflected signal is taking is very complex. It's probably reflected several times inside the canopy and then it goes back. And then the third mechanism is called the double bounce. Have you seen a geodetic prism or a corner reflector? No. The reflective surface that you have on a bicycle, it's composed of little triangles, right? Because if you have two surfaces at right angles to each other, then according to the reflection law of specular reflection, like this angle is going to be the same as this angle, and then this angle is going to be exactly 90 degrees to that one, and this is the same as this one here. And so what happens is it goes straight back. This is why you have the triangles, the prism-shaped things in the bicycle reflector. And if you are measuring with a total station, like an optical laser distance meter or something, then you're also trying to use a target surface which has these prisms in order to get a very strong reflection. And you can even create a corner reflector like this out of metal, like a big one, this size. And if you install it somewhere, you're going to get a very, very strong radar signal back from it. There's actually a place, maybe I can even show you. There's a place in Hungary called Pens. If you look it up on a Sentinel-1 image, then you can probably find a very strong reflected signal there. Okay, so the place is called Pens. It's actually not very far from here. There's a weird shaped building. Yes, this banana-shaped building just outside the village. I think this one here, which is the building of the Hungarian Geodetic Observatory. It's this place over here. Let me check the mosaic quickly because it should also show up there. Yes, I think we have it. This very bright red thing, that's the signal of a very small object. So we're talking about 10-meter pixels again, and the corner reflector is about 2 by 2 meters, but it's creating a very strong signal which you see showing up on the mosaic. Did you find it? Are you in the same place? Okay, back to the presentation. Yes, here we are. So these individual reflective ways of reflection are also influencing the polarization of the signal. We've already talked about this with Zoltan, that there's the signal is emitted in a vertically polarized way, and you're registering its intensity in the VV. So the vertically emitting and vertically registering, and the VH, vertically emitting and horizontally registering way. And so volume scattering is stronger in the VH because the reflective mechanism is complex, and so it's going to change the polarity. Double bounce is strong in the VB because it's not changing the polarity; it's being received in the same plane. Sometimes you get triple bounce, which gives a very strong signal in VH as well. So these are the sort of mechanisms that we are trying to discern when we are interpreting a radar image. This is a massive oversimplification. So radar signal interpretation is rather complex. There's many different special cases and different surfaces which reflect in weird ways. So even like radar experts who work with it every day have a lot of unknown issues with directly interpreting the signal. But sometimes it's still quite useful to see things. So if we move in, this is just a comparison between an optical image and the two registration modes of a radar image. Frankfurt Airport. So what you see here is some forests, a lake, the actual tarmac surface above the runway, some buildings here as well, a river. And so this is the cross polarization, the VH. So we expect this to reflect strongly in the forests, right? Where you have a lot of vegetation, where you have volume scattering. So the high values are coming from here. The extremely high ones are probably triple bounce reflections, so more complex direct reflections. And you have no signal whatever from the flat tarmac. Also, the lake is completely black. The river is completely black. So this is what you get for VH. And this is what you get for, okay, so this is wrong. It should be VV, so copolarization. There you had a lot of strong signals from the buildings because you have corner reflection, the vertical wall and the horizontal surface. Relatively low reflectivity still from the flat surfaces, some reflectivity from grass and from forests. This is essentially the two main kinds of signal, the VV and the VH, that we get from Sentinel-1. Every other visualization is some sort of a composite or a decision tree that we build on top of this. There's only one more trick, which is the transfer function. It could be linear, or it could be with decibels. So decibels are a logarithmic function. That means that we are squeezing very, very large ranges into a small range to be able to see the tops and the bottoms better. Corner reflection has very, very high intensity since it's sending all the intensity back to the sensor, right? And this means that if we are linearly scaling the intensity to the color, to the grayscale, then we get a few dots of very strong reflection and everything else is quite black. Yes. So we get a few dots of very strong reflection and everything else is quite black because the corner reflections have much, much higher intensity compared to everything else. But if we apply the logarithmic scale with decibels, then we see a lot more because then the range is flattened out a bit and the extremes are not so large. And so then we have a lot more information about the surface. So this is the linear gamma and this is the decibel gamma, where you have more texture. Okay, and then again, since we are looking from the side, slopes are influencing our signal very heavily, but we can use the terrain model to figure out these processes and to correct for these slopes. So what we see here is a very strong effect of the slope. We have a hill like this. The sensor is coming from over there, and that means that this part of the hill is facing away from the sensor. We're getting very, very low energy, and the pixels are sort of stretched because, if the sensor is looking from the side and trying to sample the ground in uniform units, boxes, then if you have a slope, then these boxes are going to get smaller. And if you have a slope facing the other way, then they're going to get very large. That's why we see this sort of stretch effect, right? This slope somewhere in Slovenia is facing away from my radar, but it's possible to calculate these back because this can be described very well physically. If we know the geometry, then we can sort of interpolate to smooth them away, and then we are starting to see a pattern. Okay, and the different visualizations we like to apply in Copernicus Browser are RGB ratio. enhanced visualization and Sentinel-1 urban. And this is again a comparison. This is a place in northern Denmark. So we have an area of bare sand, some agricultural areas, a town, and the sea. So with RGB ratio, we are assigning the VV to the red. So essentially the double bounces, the VH to the green, which is the volume scattering, and the ratio between VV and VH to the blue. That means that places where the volume scattering and the double bounce, or the co and the cross polarization, are very different, will be strong in the blue, like low vegetation areas. Places with a lot of volume scattering are going to be green, forests, and places with a lot of double bounce, urban areas, are going to be red. And the sea is going to be completely black. And the exciting part, this is a big sand dune. This is also nearly completely black. It has a little bit of red in the middle if you take a look, because some of the signal is reflected with a double bounce from inside the sand. It enters the ground and comes back out. This is Sentinel-1 star urban, where we are taking again the VV and assigning it to the green, and the VH per VV is assigned to the blue. I wonder, let's assign it to the red. I'll have to check. So again, this is a visualization which very strongly emphasizes the double bounces. We are trying to look at buildings, so big walls with perpendicular surfaces that have very strong reflectivity. And the enhanced visualization is actually already a decision tree. So it has a small classification built in, and then it's assigning different colors to the areas with very low reflectivity. So the sea, or the sand dune, and a lot of the greens to the built-up surfaces, and then you get the yellows and the whites for the buildings. This is sort of the way these four major visualizations work. So this is a crop cycle. It's a place in the Netherlands where we had a lot of fields. And as you see, again, the reflectivity is influenced a lot by the structure. Crops grow up, and then you have a lot of volume scattering. They are harvested, then you have specular reflection. Some crops have a very well-defined vertical structure where you get some double bounce. And then this means that the individual properties of these crops can be separate from each other. And so, yeah, these are flares that you get again from very strong corner reflectors, ships. So this is also a way to track them using the radar visualizations. So much for talking, unless there's a question at this point, and then we can go into hands-on.
And at one point, you're talking about the reflection of the corners. We are guessing to find the corner reflections in order to have the clear data to have.
No, that's different.
The benefit of the calculation of the corner reflections that you showed us with the Sentinel-2. So the Sentinel-1 with the VV and VH.
Well, knowing that the corner reflection influences the VV channel helps you separate different reflective mechanisms, so different types of land cover. But having a specific corner reflector as a target is used for geodesy, so for measuring surface uplift. So we had Sentinel-1 interferometry is a tool that you use for measuring very, very small changes in height or in distances. We're not going into Sentinel-1 interferometry in this course, unfortunately, but that's where you would use a solid diploid corner reflector where you're measuring its position again and again. I'm just checking whether anyone from the online audience has a question to this. And then meanwhile, what we want to do is to just pull up a Sentinel-1 monthly mosaic of the area we are in. So the university and the field that you have been exploring. I want to go just a bit further up towards Gödöllő. Okay, I hope everyone online is also seeing my screen. We go back to, let's have the most recent monthly mosaic. And we want to look first at the individual layers of VV and VH, just to understand this difference between the decibel gamma and the linear gamma. Let me post a share link into the chat. So what do we see? This is VV, so copolarization. Corner reflectors are going to reflect very intensively. So we have the corner reflectors mostly in the town. This is the building of the university. Actually, I can change the background to OSM and then we can compare better. Right? This is where we are at the moment. And so this is producing a very strong signal in the VV. We have these, that area was just over here. This is the experimental farm with the power line, remember? So this is quite dark in VV. It's not giving much of a signal. And the forest is also sort of medium dark. So what you see is that the intensity of the double bounce signals is a lot higher than the intensity of everything else. And so if I go over to the decibel gamma visualization, then I start seeing a lot more. Then these are less highlighted. The texture of the forest comes out. And you even see some texture inside the experimental farm. This is probably the greenhouse, right? These are the lakes, which are completely black because of specular collection. And these are sort of medium intensive because you still get some double bounce from the florist. Moving over to VH, now we see that the forest have some more intensity. The buildings are reflecting less strongly, but the lakes and the flat areas are sort of the same, quite dark. If we look at this in the linear sense, again, we see only a couple of very bright spots standing out. Those are probably, but again, only probably the triple bounces. So the ones where you are having a corner reflector, but it's changing the polarity because it's taking 3 reflections instead of 2. Right? So some buildings will stand out very, very strongly. And if I go back to the decibels, then these highlights are sort of less prominent, and we start to see the structure of the forest. These are the two main parameters that Sentinel-1 visualization works with. And now if I go over to RGB ratio, so VV is in the red channel, VH is in the green channel, and the ratio of VH over VV is in the blue. And this allows us to highlight the individual double bounces in red, which are very intensive. Places where I have both volume scattering and corner reflection in yellow. And places where there is a high difference between cross-polarization and copolarization, vegetated but flat surfaces in blue. This is the approximate interpretation guide. And again, if I zoom out, we have these bridges over the motorway are reflecting very strongly, because then you can also have like triple or quadruple bounces from the tarmac over to the bridge back. So these are giving you very strong reflections. It's our urban visualization. We are assigning cross polarization to the red, but we are applying a strong multiplication. We are assigning the copolarization to the green, and the cross polarization again to the blue, but with a different multiplication. So this is how we get these very strong purple or white shades for the buildings, and that's how we get the blue for everything else. So it's trying to sort of even out the very strong signals that you get from the corner reflection. And then you sort of see the buildings emphasized against the vegetation. And if we go back to the enhanced visualization, let me show you the exact algorithm. So this is a decision tree, right? It has a separate visualization for water and a separate one for land. And then there's a threshold that separates water from land that you can actually manually adjust. And for water, it's creating a red, green, blue composite out of the VV with 2 different multiplications and a bit of the VV multiplied by the VH. And for the land, it's taking the VH and the product of the VV. Yes, so that the double bounces are in the red, co and cross polarization multiplied are in the green, and cross polarization is in the blue. And so that's why we get a sort of a greenish hue for vegetation and the yellowish one for buildings. The nice thing with this visualization is that it's really good in discriminating water from land. So if we are looking at a flood, then we can see a lot. Let me show you a flood for a moment.
For example, sometimes we are going to assess the given prediction. And I'm going to use the like this. How we are expecting it by using this kind of images as well.
We are not using it for predicting the flood, but for mapping the flood.
I'm gonna meeting the mapping flood, then could be predicted something with the precipitation.
Well, yes, but that's flood prediction is mostly done on a precipitation model and a terrain model, and then you can estimate the amount of water that's coming to flow, the discharge, and then
But you will be able to read a map of the flooding, right?
let me get there in a second. I'm looking among the Copernicus Browser gallery for an image of a specific flood, which is going to be here in a moment. Oh yes, here we go. I've copied the link into the chat. Is it working? Do you see the image? So this is a Sentinel-1 false color composite. So the yellow one and the water surfaces are black or blue, and that means that you can look at the areas of the rivers of the floods. Yes, here we are. So this is how flood mapping works. This place here, this is flooded. This is flooded because the water surface is creating specular reflection. So you have a very low intensity there, and then it's relatively easy to separate the water from the land using just an intensity threshold, or to look at it with this kind of visualization. If you have this open on the browser, there's two things to do. Compare it with a Sentinel-1 image from like a month before, and then you will see the difference between the flood and normal conditions. And you can also compare it with Sentinel-2 image, and from the same date, and then you will see that the Sentinel-1 is seen through the clouds. Right. So this is the extent of the flooding, water highlighted in black and blue. And let me add this to compare and check an image a month before. It's slow on your side as well. Somebody is downloading movies. Does anybody already have it compared?
Which one?
Early May and early June.
But which one? The RGB reassurance or enhanced visualization?
Enhanced visualization, I think. So look, I have it here now. This is from April. This is from June. Now you see it, right? This is what we call normal conditions, sort of vegetation in the floodplains. This is a flood. Once more, vegetation in the floodplains, flood. So this is one of the main applications of Sentinel for flood mapping.
Really, in case it means the flood is now.
No, the flood is the black and blue, and the green is normal vegetation. And you see some blue over on these places. This is not a flood. This is just a relatively flat area which is reflecting in that specific geometry. I can even share this compare, and then you can explore it for a while. And meanwhile, I can pull up the Sentinel-2 image of the same place. Yeah, so this is a couple of days later from the 4th of June, but you see that it's extremely patchy with the clouds. Very difficult to actually discriminate the land and the water. I can give it a near-infrared false color to show you a bit more, but still the clouds are very heavily interfering with the flood mapping. So this is why we use, look, clouds, cloud shadows. And then somewhere down here, we have a flood, and we are trying to estimate the area that's flooded. You see a bit? This black or dark blue area is still flooded, but because of the clouds, it's very difficult to create a consistent map out of it. That's why we use Sentinel-1. There's one more place I want to show you on a Sentinel-1 mosaic. We go to Schwabad. What I want you to do is to create a time lapse of a year of data from this place, and then we can look at the changes together and we can try and explain them. I'm pasting the location in the chat. So now we all know how to create a time lapse. we have a mosaic once a month. Trying to create that offline maps cron at least January to summer, but ideally through a cold year. But then we could try and investigate the changes or the process. Okay, well, at least it's working on my side now. So this is September, October, November, December, January, March, April, and summer again. So what we see, these areas are snow, right? This is the top of a mountain range. And then we can observe the changes in the snow cover. And we can also observe some changes in the glaciers down here and the sea freezing over and then thawing out again. So these are the kind of patterns that, again, Sentinel-1 is useful for in snow and ice or in marine monitoring, because you can actually follow the patterns of the ice freezing and thawing and the water surfaces throughout time, again, without illumination and over clouds. And before we go, there's one more thing I want to show you in Sentinel-1. If we go back to Lake Balaton, we are trying to look at an individual Sentinel-1 image, so not the mosaic. Maybe just loading the latest image, actually. Right, this, here we are. Okay, so this is the 26th of November over Lake Balaton near Tihan. And we are looking at VV decibel gamma. And the lake surface is black, as usual. But some of it is white, some of it is rough. And this is because Sentinel-1 also reacts to water surface roughness. So it's possible to look at currents or wind patterns, because if the surface has waves of approximately the wavelength of Sentinel-1, like 5 centimeters, these small ripples, then it's going to reflect very strongly. And so the places where the waves are approximately this size will have a clean reflective pattern, and the others are going to be black. And this allows you to look at currents, because currents are also influencing the waves, and wind patterns as they are controlled by water surface roughness. We can create a quick time lapse and hopefully you'll find something nice. Yeah, what you see here is a wind pattern. This is the wind is coming from here. There's a wind shadow over in the north east of the peninsula. And so this is one of the water surface roughness patterns that you can nicely pick up using Sentinel-1. Trying to give you a stormy, more intensive image. Yeah. This is very characteristic for Lake Balaton. So wind coming from the northwest and going sort of perpendicular to the lake, and then you get these streaks, which are the movement of the water caused by the wind. So this is what wind looks like on Sentinel-1.